All right, welcome to section 2.4, part 2, zeros of polynomial functions. Same exact info as the last time. What we're going to learn this time, though, is how to find real zeros of polynomials using some tricks of the trade. So there's some theorems and formulas that we can use to narrow down equations that have a lot of possible zeros. Okay, so that's what we're going to do today. So the first one, it says one way to narrow down a search for real zeros is to determine an interval within which all real zeros of the function are located. That might seem confusing. This right here, the upper and lower bound test, will seem even more confusing if you try to read this. But what I'm going to do is I'm going to show you how to use this upper bound and lower bound test in an actual example. Okay. So it says step 1, graph the function to determine the interval of zeros. All right. So we want to figure out which bounds, okay, our zeros are located. So what nearest whole numbers are our zeros between. So notice we have, I'll mark them in blue, we have a 0 here and we have a 0 here. Okay, what nearest whole numbers are those between? All right, so if you notice, the one on the left is at -1, and the nearest whole number on the right is at 7. So everything is between -1 and 7. So that helped us narrow down a bunch of them, and you'll see how that does that. So that's step 1. Step 1 is to find the interval of numbers where your zeros are between, so between -1 and 7. All right. Step 2. Okay, what does it say for step 2? Step 2 says use synthetic substitution to confirm upper and lower bounds. So that's what we're going to do. We're going to do synthetic substitution with each of these numbers. So -1 will be first. So 2, -11, 2, -44, -24. Put a line, put a box. All right, so let's see. Bring down 2. Multiply, I get -2, add, I get -13, multiply, I get 13, add, I get 15, multiply, I get -15, add, I get -59, multiply, I get 59, add, I get 35. Okay, so what we've just done is we've proved that -1 is the lower bound. Okay, -1 is lower bound. And how did we do that? Notice that the signs are alternating. So this one's positive, negative, positive, negative, positive. Okay, you must have alternating signs in order to be the lower bound. So someone really smart a long time ago figured this out, that in order for it to be the lower bound, the signs must alternate in the bottom row. Okay, so it does. All right, so let's try number 7 now. Let's see what happens with 7. All right, let me get this page a little bigger here. And now what we're going to do is we're going to try 7. Same exact numbers, but we're going to do 7 in the box. So 2, -11, 2, -44, -24. Skip a line, draw a box. Okay, so bring down the 2, multiply, I get 14, add, I get 3, multiply, I get 21, add, I get 23, multiply, I get 161, add, I get 117, multiply, I get 819, and add, I get 795. Okay, so what we've now just done is, okay, we've proved that 7 is the upper bound. 7 is upper bound because all of the numbers in the bottom row are positive. If all the numbers are positive, then we know that this is the upper bound. So all numbers positive. So we have proven that all of our zeros are between 7 and -1. Okay, lower bound signs alternate, upper bound signs all stay positive. All right, so that's step 2. Step 3 now is to use the rational zero theorem to find all the zeros. Okay, and you're gonna see how this really narrows it down for us. So I'm going to copy this equation onto the next page. And we're going to do the rational zero theorem. Okay, so first thing we need to do is we need to find all of our P's and all of our Q's. Okay, so remember, our P's are all of the factors of our constant. So, so what are the factors of 24? So 1, 2, 3 goes into 24, 4 goes into 24, 6 goes into 24, 7 doesn't, 8 does, 9, 10, okay, 11, no, 12, yes, 12 goes into 24. Okay, 13, 14, 15, 16, nothing else goes into 24 except for 24. Okay, so there's our P's. Now our Q's are all the factors of our leading coefficient, so 2. So plus or minus 1 and plus or minus 2. All right, so there's our p's and our q's. Now what we need to do is we need to do all of our p's divided by our q's. So 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. 4 divided by 1, 6 divided by 1, 8 divided by 1. All of these numbers are going to be included. So 4, 6, 8, plus or minus 12, plus or minus 24. So the 1 is done. Now we need to figure out the 2's. So 1 divided by 2 is 1/2. 2 divided by 2 is 1. We already have 1. We don't need that. So these are done. This is done. 3 divided by 2 we don't have yet. 4 divided by 2 is 2. We already have that. 6 divided by 2 is 3. We already have that. 8 divided by 2 is 4. We already have that. 12 is 6. And 24 divided by 2 is 12. So we don't need any more. So these are all of our possibles. Now, this would be pretty miserable if we had to try every single one of these to figure out which one works. But what we're going to use is our interval from the last. Okay, here our interval is between -1 and 7. Okay, so which one of these numbers are in between -1 and 7? Okay, +1 and -1 are between -1 and 7. +2 is not -2, so +2 is. +3 is. +4 is. +6 is. Neither of the 8s, neither of the 12s are between -1 and 7. 24 isn't. +1/2 and -1/2 both are. And +3/2 is 1/2. So +3/2 is. Not -3/2 because that's -1/2. That's to the left of -1. So really our only options are +1, -1, 2, 3, 4, 6, +1/2, -1/2, and +3/2. Now, the nice thing about this is all we really need to do is pick the ones that are close to -1 and 7, because you can tell from the picture that this 0 is pretty close to -1. So what is the closest number in our list, okay, to -1 and 7? All right, so if you notice, let's do the upper bound one first. Which one of these numbers is closest to 7? We're going to try 6. Okay, so we're going to try 6 with our numbers. 2, -11, 2, -44, -24. Okay, and let's see if this works. We may need our calculator, so let me open that up. All right, so bring down the 2. Multiply, I get 12. Add, I get 1. Multiply, I get 6. Add, I get 8. Multiply, I get 48. Add, I get 4. Multiply, I get 24. Add, I get 0. So what do we notice? 0 is a remainder, so we now know that x minus 6 is one of my roots. Okay, perfect. All right, so that's the one on the top. Now let's do the one closest to -1. Where the one closest to -1 would be -1/2. So let's put -1/2 in the box. But now we don't need to use the original. We can use our new coefficients, 2, 1, 8, and 4, to see if this works. Okay, and our hope is that this is 0. So let's bring down the 2. 2 times -1/2 is -1. Add, you get 0. Multiply, you get 0. Add, you get 8. What's -1/2 of 8? That's -4. Add, you get 0. So what did we prove? Okay, we prove now that this is -1/2, so x plus 1/2 is a factor. And what else have we done now? So what else this has helped us do is we started with a fourth. The first 0 brought us down to a third, and the second 0 brought us down to a squared. So now what we have left over is 2x squared plus 8, because this is 0x, so 2x squared plus 8. All right, now we can use the rest of this number to get the rest of our zeros. So we already know 6 works, we already know -1/2 works, but let's do something with this. So I'm going to factor out a 2. So I'm going to take this 2 out. I'm going to rewrite x plus 1/2. I'm going to take this 2 out of here. So when I take 2 out, I get x squared plus 4. 2 divided by 2 is 1. 8 divided by 2 is 4. So I factored out a 2 here. So now what I can do is get all of my zeros. So this one's equal to 6. This one's equal to -1/2. And then this one I need to set equal to 0. And I should be able to solve that pretty easily. So subtract 4. Okay. Subtract 4, so I get, I need to extend the page here. So I get x squared equals negative 4. Take the square roots. Take the square root. Okay. And I should get x is equal to plus or minus 2i. Remember, when there's a negative underneath the square, you take your I out. And there would be our other zeros. So we have 6, negative 1/2, and plus or minus 2i. Now, the question is originally asking us for, find the real zeros. Okay. These last two here are not real. They are zeros, but they're not real ones. So really the only answers to the question are 6 and negative 1/2. But we had to test this last term to figure out if it actually worked. Okay. All right, so we're going to do this one in class. We'll save that one, and we'll do that one together. All right, last but not least, this one's a little bit easier. This is called, another way to narrow the search for zeros is the Descartes rule of signs. And this, once again, is a real fancy term here. So basically what we need to do is we need to find f of x and f of negative x and look at the sign changes. Okay, so let's look at example 1. It says describe the real zeros of this function. Okay, so I'm going to rewrite the function here. G of x equals negative 3x cubed plus 2x squared minus x plus 1. Oops, not plus 1, minus 1. All right, so what we're going to do is we're going to look for the sign changes. Okay, from here to here, it goes from negative to positive. There's one sign change. Then from the 2x squared and the minus x, there's another sign change, and then negative and a negative. So there's only 2 sign changes. Okay, and we're going to figure out what that means in a minute. Now what we need to do is we need to do g of negative x. So we need to plug in negative x everywhere we see an x. So everywhere I see an x, I'm going to plug in negative x, and we'll see why we do this in a minute. So negative x cubed plus 2 times negative x squared minus a minus x minus 1. So everywhere there was an x, I plugged in negative x. And now let's simplify and figure out how many sign changes there are. So negative x cubed is negative x. So I have a negative 3 times a negative x plus 2 times negative x squared is a positive x cubed. Sorry, squared. Don't forget that. And then negative x times a negative x is a positive x. And then we have negative 1. All right, so let's see what we get here. So, go to my notes. Okay, so we have a negative times a negative, so that's positive 3x cubed. We have a positive times a positive, it's positive 2x squared plus x minus 1. So where are our only sign changes located? So it goes from positive to positive, no sign change. Positive, positive, no sign change. But here we have a positive to a negative. So for the g of negative x, we have 1 sign change. Okay, so let's see what this is going to tell us. All right, so let's go back to this fancy definition here. All right, so if the number of positive, okay, real zeros of f is equal to the number of variations in sign of f of x. Okay, so for f of x or g of x, we had 2 sign changes. So that means there's going to be 2 real positive zeros. Okay, 2 real positive zeros. Let's see what else it says. Or less than that number by some even number. So what's our smallest even number? 2. So if we do 2 minus 2, 2 minus 2, we get 0 real positives. So those are our 2 options. We have 2 real positives or 0 real positives. All right? Now, what does the next one say? The number of negative real zeros of f is the same as the number of variations in the sign of f of negative x, or less than that number by some even number. So the number of negative reals is whatever the number is. So this means if we have 1 sign change, we have 1 negative real. Sorry, I'm going to rewrite that. It's terrible handwriting here. So we have 1 negative real, it's even worse, 0. Or less than 1 by 2. So 1 minus 2 would be negative 1. We can't have negative 1 real zeros. So we have 1 negative real 0, 2 real positive zeros, or 0 real positive zeros. Okay, those are our only options. Okay, so we're just describing it. It doesn't say solve it, it just says describe it. So I'm going to do another one of these in class. I know both of these examples can seem somewhat confusing. We'll go over these in class. Have a good day, and I'll see you tomorrow.